Well, ladies and gentlemen, here we are today. It's a hot day. I got nothing on here but my silk shirt and a smile, and Chibi, my little kitty, in the background. And we're going to talk about forecasting because I'm all dressed up and nowhere to go. At any rate, let's get on with the next slide. Uh-oh. There you go. And so what are we going to look at? What are the topics here for tonight and for this week? Well, we're going to look at these forecasting components. We're going to look at some time series and moving averages. We're going to take a look at forecasting accuracy and alpha and beta values. We're going to show you some examples for time series using Excel and for QM for Windows, but also please don't use QM for Windows as it may A, blow up, and B, people have reported a virus. And finally, we're going to go over some regression models tonight also. So, whenever we talk about these different components of forecasting, there's patterns that we are looking for in the data. And this is what a lot of decision sciences is about, looking for patterns in the data. And so there are different time frames involved. Some are snapshots, they're short range, they're only 1 to 2 months. Others are medium range, 2 months to 1 or 2 years, and others are long range of more than 2 years. Again, this would correspond with your day-to-day operations, which are short range, your tactical, which are your medium range that your middle managers use, and then your top executives use long range planning and strategic planning. So we look at those time frames. When it comes to patterns, we'll show you examples of these. There are trends. There are just random variations, which means there is no pattern. There are cycles that they go through, and there are also seasonal patterns. And we will look at all of these. So a trend is a long term. So trends have to occur over the long term of an item that is being forecast. Random variations, they're not predictable. There's no pattern. There's nothing that we can try to use our crystal ball to tell what the future is. It's random. There's nothing that can be predicted. When we look at a cycle, this is a movement up or down that repeats itself. Again, cycles occur over a rather long time span. And then seasonal patterns, these are oscillations or variations of these movements that occur in the short run. And it's repetitive, but in the short run. So, think about summer, spring, fall, winter, those oscillations, seasonal patterns in selling lawnmowers, seasonal patterns in showing snow blowers, seasonal patterns in buying turkeys. So let's take a look and move on to the next. So here again are some different ones. Notice here on the y-axis is our demand. Time is on our x-axis. And these are just random movements. There's nothing here that we can predict. They're random movements, but there is a trend upwards. In this one, for number B, is a cycle. Again, notice the cycle here that occurs every so often. And then C is seasonal. Here's a peak, for maybe turkeys that are sold around Thanksgiving time, and then another peak that are sold around Christmas time. And then here is a trend, which is seasonal. So it's a trend upward, and every so often we're getting a peak here, and this is occurring on a seasonal basis. So statistical techniques that use this historical data. We are using data from the past to predict the future. And these would be things, regression models. We'll take a look at them. These are called causal models. And we're trying to look at a mathematical relationship between the dependent and independent variables. And we've shown you this with a software engineering. So you've seen it before. We are just reiterating this again. Qualitative methods are methods that use judgment, expertise, rules of thumb, and opinion. And unfortunately, most decision making uses qualitative and not quantitative methods. So, a jury executive opinion means that this is kind of a, somebody in charge is making the decision. These are qualitative techniques. They're the most common used in forecasting. You'll see that on the test. for long-term strategic planning, performed by individuals or groups within an organization. Sometimes they call in consultants or other experts, but people that are on the top have their judgments, their opinions, and qualitatively they will make decisions based upon that. And again, they may have a specialty. I'm in marketing research. I'm in engineering. I'm in MIS, and I see, I can recognize a pattern, and I don't need math in order to prove it. These are all jury of executive opinions. And they're individuals that have experience, knowledge, gut feelings, if you will. What do we use if we use qualitative methods? Delphi technique, marketing research, surveys, those type of things that will support these qualitative methods through the quantitative methods. So, time series methods, we use historical data. It's occurred in the past, so we think it's going to continue into the future. And it's one factor that we're looking at for the most part, and that is what will happen to sales over time. So, time is the factor that we're involved with. So, again, with these moving average or values, use past values, we can dampen or smooth these. These rather, changes that are pretty quick. We can smooth those out, and we can make them relatively stable. And one of these moving averages here is for a certain number of periods, and we look at the data that starts in the initial time, and we move on from there. So this is our formula. This is a moving average. So, here again, give you an example of a paperclip supply company. They want to know, hey, how many are we going to sell in November? Well, a 3-month moving average just says that over the last 3 months, we sold 90, 110, and 130 orders, and divide that by 3, that gives us an average of 110. If we have a 5-month moving average, we would take the last 5 months, divide them by 5, and that would give us 91 orders. So you can see there's a difference between the 3-month and the 5-month moving average. So here is a 3 and a 5-month moving average. Again, we take a look here, our months, our orders per month. Now we're going to try to predict November here. Here's the last 3, here's the last 5, and so for November, if we take the last 3, 1, 2, 3, if we take the last 5, 1, 2, 3, 4, 5. So, 1, 2, 3, 4, 5. This will give us 91. The last 3, 1, 2, 3, will give us 110.0. So again, take a look here and take a look. Here's our actual. And here's the 5-month, and here's the 3-month. And so we're going to take a look at which one of these are good and bad parts. If it's a longer period moving average, they're going to react more slowly to changes than do shorter period moving average. So, it's a trial and error. This thing is not necessarily cut and dried, and moving averages do not necessarily do well with changes such as trends and seasonal effects. They are easy, inexpensive, and they're good for short-term forecasting. But again, if there are rather large variations, then we run into problems with moving averages. So we can come up now with a weighted average. And again, I told you about the papers that I'd written on order-weighted averaging. This is just a variation of these weighted averages. And so what we'll take a look here is, we take a look at the paperclip company, and we're going to give 50% for October, 33% for September, and 17% for August. Again, 50% for October, 33% for September, and 17% for August, because the further we're getting away, we're going to give it less weight. And there's 90, 110, and 130. We go back here to the previous, and there's where we're getting our information here to place in. And so it gives us, this trial and error estimation. So we can also use experimental smoothing here, where we use alpha levels. Exponential smoothing, and simple exponential smoothing, and adjusted. These are the two types. And so for the simple exponential smoothing, we have some sort of a forecast for the next period, F T plus subscript T plus 1. We have the actual demand in the present period right here. And we have an alpha for this, a weighted factor, a smoothing constant. We're going to take times this actual demand. And then we have 1 minus alpha, which is the other weighting factor, because don't forget this has to add up to 1 because this is a probability, and this 1 minus alpha is for a future time, and this is the previously determined forecast for the present period. So again, the present period, the actual demand, and the forecast for the next period with this weighting average should give us. Now again, the alpha has to be between 0.1 and 0.5. These are usually what is used, and the alpha is usually, it's judgmental, it's subjective, it's something that over time and through experience a person comes to to understand. So if we take a look here at table 15.4, which is this next table right here, and we use this exponential smoothing and a constant of 0.30, we place this in, again, 0.30, 0.70, 30, and 70, those have to add up to 100. And again, because we didn't have a time here, there was only one of these, there's only 137. We didn't have one for the time before. We have to use 37 times that for the second one. But when we got this for February, because we only had January to use, but for a 3-month for March, then we use 0.3 times 0.40, 0.7 times 37. So again, here is our, now again, that shouldn't be, see again, this should be 40 and 37. There, the graduate assistant made a mistake. And we can see here. So here's your 40. It's not 0.40, it's 40 and 37 in order to come up with March. And so we can follow along. So here again, here is your actual. Here is the alpha's 0.50, and here is the alpha of 0.30. So this gives us our exponential. So with these adjusted exponential smoothing, it's a trend adjustment that we're looking at. And again, we have another formula here, and T subscript T plus 1 plus beta F, which is the future T plus 1 minus the current time plus 1 minus beta times the time. T subscript T is the last period, and beta is the smoothing constant for the trend. So we can subjectively determine these, apply this formula, and so again, if we put this in table 15.5 here, and we take a forecast with alpha is 0.5 and beta is 0.30, then we take a look at 0.30 times 38 minus 37.0, 38 minus 37.0, and then we take a look at 38.5 minus 37.0, so 38.5 minus 37.0, and we take 0.70 times 0 because we didn't have a time before that, and we will get then 38.5 plus 0.45 is equal to 38.95 for period number 3, 38 point, again, what are we looking at? 38.95, which is right here. So let's move on. We can also have an adjusted forecast that's higher than the smooth forecast. It's more reflective of generally increasing trend in the data in this adjusted forecast. So here, take a look at the forecast with alpha is equal to 0.50 right here. The one that alpha is 0.30, and here is the actual that is occurring in between. So now we're getting into time series. Here we're getting into regression or a linear trend line, where y is equal to a plus b x. A is the intercept at period 0. It's where we intercept the y-axis. B is the slope of the line, the rise over the run. X is the time period that we're looking at, 1 month, 2 months, 3 months. And y is the forecast for that. Now, how do we come up with beta? Well, the slope of the line is equal to this summation of x times y minus n, however many we have, times the average of x times the average of y over the summation of x squared minus n times the mean of x. And a is equal to the mean of y minus this beta times the mean of x. And we can come up with a number of periods using these formulas. So this can also be done for us in SPSS, which is very simple. If we take a look here at the table on 15.6 and we look at these computer services, we can see that x bar is 78 divided by 12, 78 divided by 12, which gives us a number of 6.5, so 78 divided by 12 gives us 6.5. The mean of y is 46.42, which again is, we add up 557 and divide it by 12. 557 divided by 12 gives us the mean of x. And then the beta is this summation of x times y, so we got to take x times y. That summation gives us 3867 minus 12 times. The 6.5 is right here. The 46.42 is here. The 650 is right here. Here's your 3,867 that we have here. And we take it and put it in there. And if we're to look at time period number 13, then we're going to say that y is equal to 35.2. Where did we get our 35.2? Right here. Plus 1.72 here times 13. We are predicting for the time period 13, and that's 57.56. So we would say in time period 57.56. So this right here should be 57.56 for the next period, which is 13. So it does not adjust to changes in the trend as exponential smoothing does, and it uses shorter time frames, and so it has its limitations also. So here's the trend line, here's the actual, and these are the errors in between here of where it is missing the trend line. And this, again, assumes a linear relationship. So a seasonal pattern is repetitive. It's up and down in demand. And seasonal patterns can occur on a quarterly, monthly, weekly. Seasonal is adjusted forecast that can develop by multiplying a normal forecast by a seasonal forecast. We'll show you an example of that. And a seasonal pattern can be determined by dividing the actual demand for each season by the total annual demand. Here's the total summation demand and the individual over that. So we'll stop right here, and we will move on a little bit later with the second